In Chapter 3, we're going to look at what we call a derivative. So in 3.1, we're going to go back to the very beginning in section 2.1 when we were talking about instantaneous rates of change. And remember, that's just simply a slope of a tangent line. Now let's do a quick review. Let's just say that at this point 2, when x is equal to 2, I'm on the graph. Now, if I draw a line tangent at that point, it would look something like this. So this would be our tangent line. And that would give us an instantaneous rate of change. What it does is it gives us the rate of change at that single point, which is simply the slope of the line. Now, if I look at, say, another point on the graph, and I draw a line through these 2 points, that would be a secant line. So secant just means it passes through 2 points. Tangent means it passes through 1 point. Remember, the secant line actually just gives you an average rate of change. And that's because it's passing through 2 points instead of just 1. So geometrically, the idea is if we wanted to find the slope of the line tangent at a point, what we could do is we could just keep drawing secant lines that are getting closer and closer to our tangent line, right? And we would compute the slope of these secant lines. So the slopes of these secant lines, as it gets closer and closer to the tangent line, would just give us the limit. And that's what you computed in 2.1. So let's look at the definition for rates of change. Our average rate of change, that would be our slope of our secant line, and we just get the slope formula. The instantaneous rate of change is the slope of a tangent line, which means we're using the slope formula, but we're taking the limit as x gets closer and closer to a. Now if I wanted the equation of the tangent line, that would be this equation at the bottom here. And that's just simply the point slope equation of a line, which is y minus y sub 1, equal to the slope m times x minus x sub 1. So here note that in the first equation, the point that it's passing through is a comma f of a, which is the same as saying x sub 1, y sub 1 in that point slope equation of a line that you used from algebra. We're going to look at an alternate definition of rate of change. And this alternate definition is actually going to be what we're going to use when we compute derivatives. Derivatives is the goal of calculus. Most of calculus is based on the idea of a derivative, which is just the instantaneous rate of change. So let's just say that in the previous formula, I replace x with a plus h. So in the slope formula, you're just going to substitute a plus h for x. And then we get this alternate form. That's actually the form that we want to use. I don't know if you remember this from algebra or maybe pre-calculus, that this was actually called the difference quotient. So some of you may be familiar with that terminology. And the reason why we introduced it in algebra and in calculus, algebra and pre-calculus, is because you see it in calculus all the time. So what we're going to do is we're going to look at an example where we use both of these formulas. So in example 1, we want to find the equation of a line, okay, that's tangent. So equation of a line, I'm going to use y minus y sub 1 equal to mx minus x sub 1. So this line is going to be tangent to this function f at the point x is equal to 3. So in our formula, a is 3. So the first definition we saw is going to give us the slope of a tangent line, which would equal to the limit as x approaches a, in our case a is 3, of f of x minus f of a, which is 3, over x minus 3. So this is the limit that we're going to evaluate. This will give us the slope of our line, and then we just need our point. So this would be the limit as x goes to 3 of, now f of x is simply x squared minus 2x, and f of 3 is 3. Oops, that looks ugly, but I'll leave it, over x minus 3. So notice if I were to evaluate this limit, I would get a 0 over 0, which is an indeterminate form. And that tells me that I need to do something more. Looking in the numerator, I can see that that factors into x minus, oops, I'm going to have to erase this because I did something horrible. I left out my limit. So that would be the limit as x goes to 3 of x minus 3 x plus 1 over x minus 3. And now canceling the x minus 3 on the top and bottom, I can re-evaluate the limit and see if I get some number, which would be x plus 1. And then this limit is 4. So remember that represents the slope of our line. So we need a slope, we need a point. So if I put 3 into the function, my y value will be 3. And then the equation of the line that's tangent at x equals to 3 would be y minus 3 equal to, our slope is 4, x minus 3. So typically we would simplify this and write it in the slope-intercept form. So I'm going to get 4x minus 12, which would be y equal to 4x minus 9. And that would be the equation of a line that's tangent to our function f at the point x is equal to 3. So let's go ahead and just compute the slope using the alternate definition. So the alternate definition to find the slope of the tangent line would be the limit, and this time it's h going to 0, of f of a is 3, a plus h, minus f of 3 over h. So if I put in 3 plus h into my function, this limit as h goes to 0 is going to be 3 plus h squared minus 2 times 3 plus h minus, and here f of 3 is 3, all over h. So if I were to evaluate this limit, I would get 0 over 0. So let's go ahead and multiply out, combine like terms, kind of see where we're at. This would be 9 plus 6h plus h squared minus 6 minus 2h minus 3 all over h. Again, if I evaluate as h goes to 0, I still get the indeterminate form 0 over 0. So let's go ahead and simplify. 9 minus 6 minus 3 is gone. And typically when we're using this form of the definition, mostly everything should cancel except for the terms that have h in them. So I have the limit as h goes to 0 of 6h minus 2h would be the 4h. I'm going to write the h squared first. So I get h squared plus 4h over h. So you notice that all my terms have h in it. So again, as I evaluate as h goes to 0, I still have the indeterminate form 0 over 0. So I need to do something more. What I'm going to do is I'm going to reduce by h to get h plus 4. So now when I evaluate this limit, it's equal to 4. And that would be the alternate way to find the slope of the tangent line. And then we would finish as we did in part A to find the equation of the tangent line. That brings us to our formal definition of the derivative. So when we look at the formal definition of the derivative, it's going to be the limit as h goes to 0 of f of x plus h minus f of x over h. So we're not evaluating it at a particular point A. What this actually gives us is a function. It gives us the function of all slopes of all tangent lines. So all we have to do to evaluate the slope of a tangent line, or to find the derivative, is just to put in values for x. The notation we use, instead of writing slope of the tangent line, is this notation here. This little accent mark, that is the mark of derivative, and we use the word prime. So you can say the derivative of f, or you could say f prime. So let's go ahead and look at an example. But before that, I would like to point out some other notations that you may see. If we look at these first three, remember f of x is just a y value, so we could do y prime. Now this one is interesting, dy over dx. That's translated as the derivative of y with respect to x. Okay? And it references the variable we're using. If the variable in our function were t, it would be dy dt. Sometimes we don't put the y value in. So this is just the derivative with respect to the variable x. Sometimes we'll use a capital D to stand for derivative. And we always need to list the variable there. So this would be the derivative with respect to x. So other notations, f prime of a, if you're evaluating it at some point A, y prime of a, or if you're evaluating at a, you could see the derivative of y with respect to x evaluated when x is equal to a, or similarly the derivative with respect to x evaluated when x is equal to a, and then the derivative with respect to x, and so on. In example 2, we have this function f of x is equal to the square root of x plus 3. We want to find the derivative. So when we find the derivative, in this section, we have to use that limit definition. So the derivative of f of x is going to be equal to the limit, as h goes to 0, of f of x plus h minus f of x over h, which again is that difference quotient from algebra or pre-calculus. So now it's just a matter of substituting for the f of x and the f of x plus h. This would be the limit as h goes to 0 of the square root of x plus h plus 3 minus the square root of x plus 3 all over h. If I were to evaluate this by putting in 0 for h, I would get 0 over 0, which again is an indeterminate form. So I need to do something else. And the something else that I'm going to do is I'm going to multiply the top and bottom by the conjugate, and I'm going to rationalize the numerator. Typically we rationalize denominators, but we can just as easily rationalize a numerator. Which means I'm going to multiply top and bottom by the same thing, but its conjugate, which would be the minus goes to plus. A lot of calculus is simply using algebra techniques. So sometimes people are not too successful at calculus because they've forgotten their algebra. Now in the denominator, I'm not going to multiply through by the h. I'm going to leave everything factored for now, because something might cancel. Okay, so I've multiplied the top and bottom by the conjugate. Now in the numerator, this is just going to simplify to x plus h plus 3. The middle terms will go away, and then I'll get a minus x plus 3. All over this nasty looking denominator. Okay. So in the numerator, this is going to cancel, right? X minus x is gone. And this is going to be a 3 minus 3, so that's gone. And now my limit as h goes to 0 will be h, over h times this hot mess. You see why I left it factored? It's easier for me to reduce. So I could see that the h's will cancel. And then I'm just evaluating this limit as h goes to 0 of 1 over the square root of x plus h plus 3 plus square root of x plus 3. So that's just going to be 1 over 2 times the square root of x plus 3. So this is our derivative. And that was part A. So in part B, the question is, for what x is there a horizontal tangent line, if any? So think about this. If a line is horizontal, that means the slope is equal to 0. And the slope is equal to the derivative. Oops, sorry. Which means that if we set our derivative 1 over 2 times the square root of x plus 3 equal to 0, then we can find out if there's any line tangent with a horizontal tangent line, so slope of 0. If I were to solve this equation, I get 1 is equal to 0, which is not true, that's false. So since there's no solution to this equation, what that means is that there's no point where there's a horizontal tangent line. So there's no horizontal tangent line. Okay. So we have some alternate notation for a derivative. This is the Leibniz notation. It's not used very often. But here we're looking at replacing the h with this triangle and x. Okay, so remember in our previous definition that was our h. And so we're looking at this symbol, triangle x. So this triangle is a Greek letter delta, and it's the uppercase delta. When we were doing the epsilon delta definition with limits, that was a lowercase delta. And typically we use delta to describe a change. So this would be the change in y over the change in x, which is simply the slope, right? We subtract our y's over subtract your x's. Now, I typically don't use this notation very much, but if you look at some really old math books, they'll use the Leibniz notation because it was one of the first notations we used when we were talking about derivatives. Let's look at when f is not differentiable graphically. So first of all, one of the criteria for being differentiable means you have to be continuous. Remember, we're trying to find a rate of change. If there's a hole or a break in the graph, there's no way we can find out how this graph is changing. So if your function is not continuous at some point, then it's not differentiable at that point. If your function has what's called a corner or a cusp at A, and that would be like a corner would kind of look like a V, or a cusp would be something that has, looks like curves coming together. This is an example of not differentiable. And the reason why is because remember, we're looking at a slope of a tangent line. If you look to the left of A, this is going to have a different tangent line than the right of A. So you have two different tangent lines. That means you have two different rates of change, which can't happen. And then similarly with this cusp, you look at the tangent lines, and what happens is you have two different tangent lines. Okay? And again, that can't happen. So another thing we could see is something with a vertical tangent line. Vertical tangent lines, well, first of all, vertical lines, the slope is undefined, which means the derivative is undefined. So if you look at a cusp that comes in very deep, that would be an example of a vertical tangent line, because if you come in from the left and you come in from the right, the tangent line actually is a vertical line. Okay? Which means that you have an undefined slope. And the slope is the derivative, so undefined derivative. In the previous cases, we have two different slopes. So what is the relationship with continuous functions and differentiable functions? In theorem 3.1, it says that differentiable implies continuous, which means that if a function is differentiable, then it's also continuous. This does not work in reverse. Just because a function is continuous does not mean it's differentiable. And you can go ahead and look at those three examples we had previously. When you look at corner, cusp, vertical, tangent, all those graphs are continuous at A. They're just not differentiable. However, if a function is not continuous, then it's definitely not differentiable. So they're just some ideas or theorems that may come up. So what we're going to do is, my graph came out really gray on that other one, the blank graph. What we're going to do is we're going to look at a function by its graph and see if we can graph the derivative. So just a reminder that the derivative is a function. Okay? What you want to do when you graph the derivative of a function is you want to look at peaks and valleys. So when I look at example 3, I have this graph. And I notice that there's some peaks, some valleys, some peaks, some valleys, and then I'm looking at the endpoints as well. And now let's look in between these points. So let's see, what is this? 1, 2, -3. And this would be -5. From x is equal to -5 to x is equal to -3, remember the derivative is a slope. So if you think about any point here in between the -5 and the 3, and you draw a tangent line, then the slope at that point would be -1. So going on my dark graph, which I have no idea why it's so dark, I'm going to go to 1 to -3, and then the -5, and I'm going to graph the slope of -1. Let's see if the blue shows up. Maybe I'll do a thick line. Okay. Now, we have to remember that at the ends, it's an open circle because of these sharp corners. It's not differentiable. So when I graph the derivative, I need to leave that open. Also, something to note is at endpoints of your graph, not differentiable. It doesn't make sense to talk about how a function is changing if you've only got one side of the function. So let's go ahead and look on our graph between -3 and 0. And think about at all points here, what would be the tangent line? What would be the slope of the tangent line? And the slope here is 1. So when I go to my graph of the derivative, from -3 to 0, oh shoot, look at what I did. I made an error. I made this, which shouldn't be there. Sorry. So it should just stop here at -3. Well, that's pretty bad. Okay, so when we go from -3 to 0, the slope is going to be 1. So I'm going to graph 1 for the slope. Now remember that it's not differentiable at the end, so open circle. So when we go from 0 to 1 to +3, and we look at the slope of a line tangent at any point, when we compute the slope there, it should be -2. And if you don't see how I'm getting that, remember that you can always do rise over run. Pick any nice points on this graph, right? Here's a nice point, here's a nice point. So I would have to go down 2, so that's a -2, and over a +1. So it's -2 over 1. From 0 to 3, I'm graphing -2. Again, remembering that it's an open circle at the endpoints. And then looking at this last piece from 3 to 5. It looks like the slope is positive 1/2. Okay, so that's going to be a positive 1/2. Again, don't include the endpoints, not differentiable at endpoints. So this is an example of where we're going to take a graph of a function and graph the function's derivative, which again is a function that we can graph. Let's look at example 4. And here I'm going to assume here that this function's going to go on forever and ever, which it does if you look at the equation for g. And I'm going to go ahead and I'm going to sketch the graph of the derivative directly on this graph. So again, what I want to look for is I want to look at for my peaks and valleys. This is a nice smooth graph. There are no sharp corners, there's no cusp. It's differentiable everywhere. So when you think about these peaks and valleys, think about what the tangent line would look like. These would be horizontal tangent lines. And a horizontal tangent line has a slope of 0. So if I'm graphing the slope, it would be on the x-axis, right, where y is equal to 0. So again, this is my function g. I'm going to graph the derivative. Let's look at -infinity to -1. Think about points on this graph. And think about drawing a tangent line and looking at its slope. So if I were to draw tangent lines, they all go down because the graph goes down. So the slope is negative. Unlike the previous example where I could find a definite slope because those were line segments, this is not. This is a curved graph. So what I can see though is as I go from -infinity and I'm approaching 1, the slope here, they're really steep but negative, right? Steep and negative, steep and negative. As I get closer and closer to -1, these tangent lines have slopes getting closer and closer to 0. Okay, so again, I'm graphing the slopes. The slopes are negative, so the graph would go below the y-axis, and the slopes themselves are approaching the 0 value. Okay. Now my graphs are really not going to be to scale, but let's look at between -1 and 0. Notice that if I look at any point and I look at the graph of a tangent line, the slopes are going to be positive. So it starts out with a small positive slope, gets steep, and then it starts leveling off again at 0 and approaching a slope of 0. So it's going to go up and then it's going to come back down. And I'm just looking at the basic shape here. From 0 to 1, again, the slopes are going to be negative as we come down and look at tangent lines. And then they're going to approach a slope of 0 here. So negative would be below, and then come up to 0. Again, this is just a sketch. And then from 1 to infinity, we have positive slopes for our tangent lines, and the tangent lines are getting steeper and steeper. So the slopes are approaching infinity as well, positive infinity. So that would be the derivative, the graph of the derivative. Okay, so let's do a last example where I'm going to have a graph, and then I'm going to decide where it's differentiable and not differentiable. So the first thing I need to do is I need to sketch my graph. So when x is less than 1, so here I'm at 1, This is going to be a graph of a parabola opening downward with the vertex at the origin. So if I just plot some points, I'll have something that looks like this. But it's an open circle, right? Because it's not less than or equal to 1, it's strictly less than 1. Oops. So here's my piecewise graph, and it's just a sketch. You can get more points if you want. Now, when x is greater than or equal to 1, I'm graphing the line x minus 2, which means at 1, we're at negative 1. Oh, so this becomes a solid dot. And then you get some points, and you'll have a line going up. So if I look at this graph, it's a continuous graph. But notice at 1, it's not differentiable, because there's actually a combination of a cusp and a corner. So it's not going to be differentiable at 1, which is our part B. Where is f differentiable? Where is it not differentiable? So it's not going to be differentiable at x equal to 1. It's going to be differentiable everywhere else. Okay? So it is differentiable, and here I'm going to list intervals from x is equal to negative infinity to 1 with a parenthesis because it's not differentiable at 1. And I don't use a union symbol, I use a comma because I'm just listing intervals where it's differentiable. And then from 1 to positive infinity. Okay, so that's the last example in this section. And that's it.